Hello, everyone. I'm TC. I'm an earth scientist at the Pacific Northwest National Lab in the US. And today I'll be giving an overview of the chapter I led for the EEFA book on heat islands. This is chapter A1.5, and you can find it if you go to the link here. And also you can look at these slides. Here is the link to the slide, which I already added to the chat. But in case you did not get that, you can kind of write it down now. I'm going to talk about the outline of this presentation. First, I will be giving a chapter overview. Then I'll be giving an understanding of the theory behind measuring urban heat islands from satellite images. And finally, we will go into some practical exercises where I will go through the different scripts on the Earth Engine code editor so that you can understand the different steps I'm taking to calculate the urban heat island. So this is a chapter overview. The goal here is to learn about urban heat islands and how they can be calculated from satellite measurements of thermal radiation from the Earth's surface. And there are three main learning outcomes. First, understanding how to derive land surface temperature. Second, how to generate urban and rural references to isolate the local impact of urbanization on this land surface temperature. And finally, calculating the surface urban heat island intensity. So this is an applications chapter. So it assumes you know a bit about the fundamentals of satellite remote sensing. So there's a list of different things and kind of processes and functions and theory you do need to know to fully understand what's going on in this chapter. And if you go through it while you're going through the book, you should find it easy enough to understand. All right, let's start with the theory. So satellites can give us something called land surface temperature by measuring the thermal radiation coming out of the Earth's surface. Satellites basically measure emissions in the thermal band from space, and then they can convert these emissions into land surface temperature. The advantage here is that because satellites are pretty much continuously monitoring the Earth's surface, you can get spatially continuous estimates of this land surface temperature, which is particularly important for urban areas where we don't have a lot of measurements. There are a lot of moving pieces, as you can see from this schematic. The satellites are basically measuring the radiation at the top of the atmosphere. We then need to adjust for how much the thermal radiation is being actually emitted by the atmosphere and correct for that to get to the amount of radiation being actually emitted from the surface. And then we kind of back calculate the actual temperature of the surface. Another thing to note here is that what is land surface temperature is a directional view of surface temperature because most surfaces tend to be anisotropic. That means they give different emissions when looked at from different angles. So the angle of the satellite actually has an impact on what is the surface temperature you retrieve. So the main thing we are going to be talking about here is the urban heat island effect. So urbanization generally raises the local temperature compared to their surroundings. And this means that urban areas tend to be hotter than the background rural reference. And satellites, because they're spatially continuous measurements, can give you a better understanding of the temperature of the entire urban surface, including any intra-urban variability. What we measure here using satellites, because we are measuring land surface temperature, is the surface urban heat island. This is unlike the canopy urban heat island where you need measurements of air temperature. The important part about measuring urban heat islands is isolating this local urban temperature signal from what's happening in the surroundings. Because there are a lot of regional differences in climate, for instance, if you're near the coast, there is a constant gradient from the coastline to the inland. It is important to make sure we minimize the impact of that background variation. So one way this is done is by creating these buffers around urban areas. They are not necessarily ideal in all cases. You see an example here where if you create a buffer around Beijing, you have a lot of non-urban areas around the urban core, which is what you want. But if you do the same thing over Tokyo, you have a bunch of basically urban built up areas right around the actual administrative boundary of the city. So I'll be talking about this common method as well as some other methods to calculate the urban heat island in this chapter. So if you have attended any of the previous videos, or if you already have access to the book, you should have access to this code repository. If not, you can just click on this and accept this, and it should be added to your scripts in the JavaScript code editor. So you can just like click on this, and you should be able to see those scripts under the reader directory. So let me go here. So there's these. Here are the projects, GE Edu book, and then all of the chapters and their associated scripts and modules. So here's the one on heat islands, A1.5, and there are like 5 checkpoints here, which I will go through the presentation. All right, let's start with the practical exercise. So section 1 focuses on deriving land surface temperature. So there are 3 different things we do here. First, we process the MODIS land surface temperature products to get the land surface temperature over New Haven, Connecticut, which is going to be our region of interest for this particular example. Then we also look at processing the Landsat raw data to estimate the land surface temperature. This uses a very simple empirical equation to estimate land surface temperature from the brightness temperature in the measurements. And finally, we will talk about using the Landsat land surface temperature module, which was created by Sofia Ermida to estimate land surface temperature without having to choose your own empirical method. So this particular module uses the statistical monowindow algorithm. So you can go to the code checkout on this link. But I think what I'm going to do instead is I'm going to go through each individual code checkout. So this code checkout has actually 3 different code checkouts in it. So let me come here. I think you can see my tab, the Earth Engine code editor here. So I will start with the first checkpoint, and I will kind of go through the different steps to estimate the land surface temperature from MODIS. So first, I don't know if you can see this. I'm going to make this a little bigger. We are going to be loading in the feature collection of the New Haven census tracts, which is our region of interest. And note that these are census tracts, not the boundary of the whole city. So what we do here is that we do a dot union operation, which combines all of the census tracts into one single polygon, which is what we will be working with from now on. We also set the center of the map to be over New Haven with the zoom level. I'm sure you know what these things mean. And I'm going to add this layer to the map. So let me run this. And you can see basically this is the region of interest that we are interested in of New Haven, Connecticut. And it's been added to the map. Next, we load in the MODIS LST product. So this is, well, there are different versions of it. So this is version 6. And this is MYD, so this is from the Aqua satellite. And this is the daily product, if I am not, this is the 8-day product. And once we load in the product, we then select the particular band we are interested in. In this case, we are interested in the LST_day_1 kilometer band. So we select this using the .select operation. So what we are interested in, not just land surface temperature at all times, but specifically for the summer, Northern Hemisphere summer between 2014 and in the start of 2019. So we first create a day of the year filter. What this does is it basically filters the data based on the Julian day. So essentially from 152 to 243 day, that basically covers June, July, and August for a non-leap year, and that is corresponding to the accepted definition for the Northern Hemisphere summer. So we load in the land surface temperature variable, which we already have here. This is only for LST day 1 kilometer. We use a filter data operation to only select the images between 2014 and the start of 2019. So essentially it ends at the end of 2018. And then we use the .filter.sum filter to only select the images which are in summer. We want to create a mean of all of these images. So we just do the dot mean operation. And then we multiply this by this 0.02, and this 0.02 is a scaling factor. So if you, so this one, I think, good thing about Earth Engine, at least in my opinion, is that a lot of these ways of uh, documenting the data is very standardized. So you can kind of go to any of these data sets, go to bands, and you can find like, this is the scaling for this particular band. And there are also sometimes offsets. I don't think we will deal with any offsets in this particular case, but I can show an example for Landsat collection 2, where you have both offset and scale. So that's why we are kind of multiplying this with the scaling factor. This converts the digital numbers to the land surface temperature. Then what we do is we create a water mask. We don't necessarily care about what's happening over water bodies, because the urban heat island effect is essentially urban land cover transition process. So we load in the JRC global surface water dataset and create a mask for surface water where it's consistent over the entire time period of the dataset. So then what we do is we clip to the region of interest. So we are only interested in New Haven, Connecticut. We subtract 273.15. This is because we're converting from Kelvin to degree C. Again, if you go here, you should see that the units are in Kelvin. So that's why we are subtracting by 273.15. And then we use an update mask, not water, to remove all pixels which are considered water by the global surface water dataset. And then we add this layer to the map. And let me just run this. And you should see basically the mode. You can kind of see the modus pixels here. They're pretty big compared to the city. You can still pick up some variability. So you can see like the middle of the city has higher land surface temperature than the outskirts. This is the range I have given is 25 to 38, which I determined just for the visualization. All right, so that was the first checkpoint, which was for modus. Let's now, I don't want to change anything. Let's now go to the second checkpoint. So the second checkpoint still goes to the first steps. So it goes still adding land surface temperature modus to this map. The next thing we will do is we'll load in the Landsat collection 2 data for the top of the atmosphere reflectances and emissions. We will again do a filter bounds to the region of interest. So you might have different Landsat tiles which fall over that New Haven region for different overpasses. That's why we do a filter bound. We then do a filter date for the same period. Again, a filter dot summer filter to get only the values for summer. And then we do a cloud mask algorithm. Landsat generally does have a lot more issues with cloud contamination. So earlier we were using the Modus 8-day LST product because at the 8-day, they already choose the best pixels for that entire 8-day period. So that reduces the impact of cloud contamination. If you had used the daily Modus product or the raw product, you would do some quality control based on the cloud presence quality flags in the Modus data as well. So what I do here is I just do a simple cloud score and I choose the particular images with less than 10% cloud cover according to this cloud score algorithm. And then I just subset the total number of images to get this final collection. Here I do a dot median operation. The reason we do dot median instead of dot mean is that dot mean is affected a lot by outliers, and you would expect, even with the 10% cloud score, you would expect some cloud contamination. That's why dot median is a good way to like remove some of the impacts of clouds. If you know, like clouds have high reflectances in pretty much all wavelengths, which means that it has very high values, which would affect the mean more than the median. So median is often used as a very simple way to remove the impact of clouds. Then what I do is I select this band B10. This is band 10, which corresponds to the thermal band in Landsat 8. So Landsat 8 also has a different thermal band, B11, but we will primarily use B10 because B11 has some other calibration issues. We will clip it to the region of interest and then use the same update, not water mass, and then add this to the code editor. What then we will do next is we need to, so this is brightness temperature. Brightness temperature is not the same thing as the land surface temperature. Brightness temperature is the temperature of an object based on the emitted thermal radiation, assuming that the object is a black body. And note that this brightness temperature is for the top of the atmosphere. So to get to the actual land surface temperature, first we need to adjust for the actual emissivity of the surface. And we also need to use an algorithm to get from top of the atmosphere values to the surface values. So to get to emissivity, we will use a normalized difference vegetation index based method. So similar to LST, we calculate NDVI. This is very simple, like we load in the image collection. Here we are loading in the surface reflectances. And then we are doing, again, filter bounds, filter date, summer filter, median, and then the dot normalized difference operation between the near infrared and the red bands to get the NDVI image. And then again, we clip to region of interest and update so that we only update the mask to only use like the non-water pixels. We also add this to the map, and I will show all of those at once. The next thing we will do is find the minimum and maximum value of the NDVI within the region of interest. So we generate a reduced region. So we do a reduced region operation and use a new reducer where we combine a minimum reducer with a maximum reducer. So this is like e.reducer.min, then dot combine with a second reducer, which is e.reducer.max. And then we do a shared input true so that when you get the output, you get both values for the maximum and the minimum. Then this is the region of interest, and this is the scale and the maximum pixels, which we need to, well, I don't know if we needed to provide it here, but for very large regions, you would have to increase from the default number of maximum pixels to do these analysis. And then we can print this to get the minimum and maximum values. So let me just run this till now. So here is the minimum and maximum NDVI, by the way. So when I printed this, this is what I get. And here you can see the Landsat brightness temperature. So this is again top of the atmosphere values, and then the NDVI. NDVI is again, the whiter values are actually higher. So you have more NDVI in the outskirts of the city, less NDVI here, which makes sense because this is more urbanized. All right. So we have the minimum and maximum NDVI values. What we will do next is we will calculate the fractional vegetation. So again, this is an empirical equation where we use the maximum and minimum NDVI values to get an estimate of a fractional vegetation. This is going to be used in the next step, which is to calculate the emissivity. To calculate the emissivity, we do this very simple equation where we are multiplying the fractional vegetation with these two empirical coefficients. So we are multiplying first with this coefficient, then adding this, and then this gives us the emissivity for the surface. And let me show this as well. And generally what you will see is that the emissivity is kind of inversely related to the vegetation. Vegetation tends to have very high emissivity, like closer to 0.99-ish, almost 1, while urban areas tend to have a somewhat lower emissivity. So you can see higher emissivity outside and lower emissivity in the middle of the city. This is expected, but also to note that emissivity curves are not very well calibrated for urban areas, especially in the remote sensing context. So the next thing we will do is we will calculate the land surface temperature from this emissivity and the brightness temperature. There are many different methods to do this. This is something I chose just as an example. So you can look at different algorithms in the scientific literature and find a bunch of them. So here, if you know brightness temperature, you know the emissivity, you can get the land surface temperature. And these are basically the empirical coefficients specific for Landsat 8, but there are different empirical coefficients which have been determined for different algorithms for different Landsat satellites. So Landsat 5 has a different one, 7 would have a different one, and so on. And finally, we just add this particular Landsat land surface temperature to the right. So it might take a little, okay, it's here. So again, it does show similar-ish values to MODIS. MODIS is, showing similar variability, but Landsat has much finer resolution, so you can make out a lot more features than MODIS. All right, so that's the second one. The third one, which is checkpoint C, or the third checkpoint, we are still going to do all the same things, but we then will load in this module. I don't know if there has been much talk about module in this book, but basically Earth Engine allows you to create these functions essentially, which you can store as separate scripts and call them whenever you need them. They're similar to functions or libraries you can create in other programming languages and kind of store separately or save separately. It makes it easier because you don't have to write the function every time in a script. So you basically load in this particular module. So note that this is one version of the module, which I basically copy pasted from the one that Sophia made for her book. I think is the same current with the version she has right now. But ideally, I would just ask you to add her module to your code repository and use it directly, because she may update it in the future, which I don't know if we will do, or we might, I don't know yet. But I would just suggest going directly for the original module. So we load in the module. In the module, we have to give certain parameters to call the function. So we give the geometry, which is again our New Haven shapefile. We note the satellite name. We note the date start and the date end. And we also use NDVI equal to true. So when use NDVI is turned to true, it uses NDVI to calculate the emissivity. Similar to what we did, but not exactly the same algorithm. If you make it false, it will just use the emissivity from Aster. So that's more closer to the bare soil emissivity. And then I run this, call this module. So I do Landsat lst.collection, then give it all of the parameters. It gives you this output. And within that output, there are many different variables, but what we're interested in is LST. So we do .select LST. We again filter to some filter. We do the median. We clip to the region of interest, update the water pixels, and then subtract by 273.15 to get it in degree C. I am not going to run it again. It looks very similar. I'm going to go on to the next section. So that was the first section. The next section is how to define urban and rural references. So here I'm going to talk about 3 different ways. One is using a constant distance buffer as the rural reference. This has been very common in the remote sensing and urban climate community for a while, but there are other ways as well. So the second one I'm going to be talking about is generating a normalized buffer for an urban area using a nested function. So there are a few steps there, and I'm going to go through that. And then finally, I want to talk about the simplified urban extent algorithm, which is something I came up with a couple of years ago. It doesn't use any buffers, but has different assumptions about urban heat islands and what it means to estimate urban heat islands. I'm going to talk about that when I go to the code editor. So let me go back to the code editor. So I think you can see the code editor again. So let's go to the 4th checkpoint, which has all of the different algorithms for defining the rural reference. I'm going to skip all of the stuff we already discussed. So that's still, we calculate the Landsat land surface temperature from the SMW, or that's the statistical mono window algorithm. So that's done. So what we do is we write a function first to create a constant distance buffer. This is very simple. In the function, it takes any feature you give it. It creates a buffer of Here I choose 2000 meter or 2 kilometer. There is no very strong reason to choose 2 kilometer versus 10 kilometer, but people have used a bunch of different values in the literature. And then we do a dot difference because the buffer is going to include the original geometry, but you want to remove that geometry to get only the rural outskirts, right? So that's why you do a dot difference and then you return this. So this gives you the rural reference variable. So if I add this to the map, so I think this is going to start taking a long time to run just because there are so many things happening at once. But if it does not run, I have put some images on the, oh wait, it is running. So this green part is that 2 kilometer buffer around the urban area, which you can see here. All right, so that's the first method of doing it. The second method of doing it is creating a normalized buffer. So the way this starts is this is an iterative method, at least in Earth Engine. I don't know if there's a better way to do this. I have been using this for a while and it generally works. So what I do first is we start with a list of distances. So here I start from 30 and go up to 3000 with a step size of 30. So that's the ee.list.sequence. So it goes like 30, 60, 90, and so on and so forth till 3000, which is a lot. But usually you don't have to go that far. For smaller regions, it just does not need to be that big of a maximum value. So this is where I am calling the function, and I'm going to go through like what the function is doing. So we are doing region int, which is the original New Haven shapefile or feature collection in this case, .map buffer optimize. So it first goes into the buffer optimize function. Within this, the first thing that it does is it creates this variable called buffed, which is ee.feature collection of the buff widths values. So we had these buff widths values, which is a sequence of numbers. We've converted these into a feature collection and map, well, this is happening in the same step. So we basically call a function called buff. So what does the buff function do? For each of those values, so buff length is each of those values, and this is like the internal local variable that it's using. It's going to create a buffer for the original polygon, and it's going to set the buffer width as the number being 30, 60, 90, and so on. This is just a property. Then what it's going to do is, again, it's going to create the difference because we want to only look at the outskirts, not the urban area plus the buffer. So we do the difference, then we calculate the area. Then we do another difference. Here, what we do is we so first is to create the area, and the second is to create the geometry with the inner urban area removed. And then what we do here is we find the difference in area between the original urban feature collection and the new buffer that's created. So you're essentially, what you're doing here is that for each of those lengths, you are generating a difference in area between the original urban area and the buffer created using that length. So that's a lot of different values, and that all gets turned into this feature collection. Then what we do is we sort this feature collection by this buffer difference value, which is the difference in area. So when you sort this is by ascending order. So the smallest value is at the top. And then we choose the first of that sorted feature collection, which means we are choosing the feature which has the least difference from the original urban area, if that makes sense. So if you say the buffer with the distance of 90 has the least difference in area with the original urban area, then we are choosing that particular buffer. And then we set this particular buffer as the main output feature and give it some of the properties from the original calculation, like the area of the urban area, the area of the width of the buffer, and so on. So this creates the normalized rural reference. So there's like a lot of stuff going on in that. I will try to run this, and I don't know if it will run in time. But if not, let me switch back. If not, you can actually see this brown area is actually the normalized rural reference, which tells us that this is actually much lower than the 2000 meter we gave earlier. So this seems to be closer to like, I don't know, 1100, 1200. I have to check if I run it, if it runs and does not blow up. But it usually does run. It just takes a little bit of time. So that was basically section 2, where I go through the different ways to standardize the urban area and its rural reference. While this runs, I'm going to go back to the other tab. So let us now talk about the third and final section. So this is calculating the surface urban heat island intensity. So this is very simple. Like we already did most of the work, but basically what we are going to be doing here is we are going to take the average value of LST over the urban feature collection, and then the average value of LST over the rural area, which is either the buffered constant buffer area or the normalized buffer area. The other thing that we will do here is we will also talk about the simplified urban extent algorithm. So let's go back to the other, to the code editor. So we are back here, and I am trying to see if they have the value. It doesn't have the value here. Okay, so the next thing we will do here is what the simplified urban extent algorithm does is that, assuming you know the urban extent, this is not necessarily the urban administrative boundary, which is what we are doing here just for simplification. You would ideally want to do this with a physical boundary of urban areas. We will separate out the pixels which are urban and the pixels which are non-water and non-water and non-urban. And then we will calculate the urban LST average and the rural LST average and subtract those. So that's what we do here. We are using the NLCD land cover dataset as our classification to separate urban and non-urban. So for urban, we first choose all land cover. So we are, sorry. So for urban, we are basically just giving creating a temporary variable here, which is equal to the original land cover dataset that we loaded in. For urban, we update the mask to equal what is classed as number 23 and 24. So if I go to here, I think this is medium and high density, if I remember correctly. Yeah, so this is developed medium and high density, and this is developed high density. So we are choosing only these two to define our urban pixels. And then for non-urban, we first create a list of possible classes, and then we find the values which are equal to these particular classes. And then we update the mask again. So these are 41, 42, 43. I don't remember exactly what they are, but a bunch of them are water and wetlands and stuff. So these are like forests, deciduous, evergreen, mixed forests, and so on. And I think some are here are woody wetlands, emergent herbaceous wetlands, cultivated crops, and so on. So we remove all of these, or rather we combine all of these and create our non-urban pixels. So when I run all of this, you can see what the urban and non-urban pixels are. So these are the urban pixels within New Haven. These are the non-urban pixels. So we will be using the LST over these as the rural reference and the LST over these as the urban reference. And then so finally, we will be calculating the surface urban heat island intensity using these three different methods. And for that, let's go back to the code editor once more. So this is the final checkpoint, which will, of course, go through all of the original scripts and, and then calculate the urban heat island. So I'm going to skip all that, come here, and somewhere here. You're right. So this is where we created the urban pixels and non-urban pixels for the simplified urban extent algorithm. Uh, what we do here is very simple. We create a function. We create only one function to calculate the urban heat island for all different cases. There are a few different things I'm doing here. So first, we are taking the LST final image, subtracting 273.15 to get to degree C, updating with the water pixels so that you choose all non-water pixels, and then doing a reduced region to get the mean value over that entire geometry, which is the New Haven feature collection. The other thing I'm doing is very similar, but in this case, we are also updating with the urban mask. So we are only choosing the urban pixels when doing the reduced region. This is what I would recommend in all cases because administrative boundaries of urban areas can have non-urban land cover, which we don't necessarily want to include in when calculating the urban heat island. Uh, Similarly, what we are doing for rural reference is that, okay, so we are also doing a LST final here with a different scale size just to make it faster as well. And then finally here we are looking at the Landsat. Okay, Landsat comp was, this is a bunch of different ones. Oh, this is from the Sophia's algorithm. So we are basically going through all of the different algorithms so that we can compare. I'm not doing the comparison here, but this is to show like one function where everything is called in. And then here we are calculating the same, but for rural reference. So we are updating the mask to include the urban, non-urban to get the rural reference. And then we are doing the same thing with the other Landsat image created from the second algorithm. So all of this is then returned as different properties when you call the function. So this basically gives you all of the urban values as well as some of the rural values, such as the one from for the simplified urban extent algorithm. And then finally, we calculate the same LST values for the rural reference. So here we have two different rural references. One we created using the 2000 meter or 2 kilometer buffer, and then another we created using the normalized buffer. So in both cases, we are mapping to the same function, which is ref mean. And it's very similar. Instead of using the urban feature, it's using the rural feature to calculate the urban or rural LST. And then here at the end, we are basically going to be printing these values to show, what the urban heat island intensity is. And we will also, in this case, create this image so that you can see the spatial distribution of the urban heat island. The way we do this is we first take the original Landsat image. So here we are using the second version, which is the one from the land surface temperature module. We are updating mask to only include the urban pixels. And then we are subtracting the value of the rural reference, which we calculated for the whole region. So this was from this particular analysis. And what we are doing is that we are subtracting that same reference from all of the land LST values. And that will give you a spatial distribution of the surface urban heat island. And all of that should be added soon. So this will take a bit of time to run. But if I go back to the other script here, other tab here, this is what it should look like. I forgot the exact range here, but you can go to the script and check. But this gives you kind of a spatial variability of the surface urban heat island intensity over New Haven from this algorithm. It's still kind of running, but I think that's basically the overview of it. And I am going to stop at this point. and kind of come back here. And if you have any questions, do let me know.